relation between the states, the rates at which one turn into another. So it looks like they're made out of just 3 quarks. Then there's this other class of particles which are called mesons. The first class were called baryons. The words aren't going to do you any good. But the other class of mesons we have to understand as being made of a quark, 1 quark and 1 antiquark. An antiquark is a negative particle with all the numbers, all the charge properties, the exact opposite of a quark. We make a quark and an antiquark, put those together, we understand the meson states. Put 3 quarks together, we understand all the others. So we have made a really great progress in analyzing these patterns. So much so that it looks very much as if, to me at least, that we're very close to understanding this part of physics, this strongly interacting system.
But what's the main barrier still to?
Well, the quarks have... Well, the main barrier is we don't understand it quantitatively. We don't know exactly the laws. I mean, we do things like I'm just talking to you on a little bit more carefully, counting how many states we should get and so on, but we don't know exactly how they move and exactly what holds them together and so on and so on. Also, there are a number of paradoxes with this quark picture. This picture helps to give us a behavior at low energies of what kinds of particles to expect. But then you'd expect that a particle would be made out of only 3 parts. But we've done some experiments at very high energy, hitting a proton with an electron, which can only be interpreted by supposing that the number of particles inside is really infinite. If there are particles inside, it can't be done with just 3. You can calculate, it doesn't come out right. So there's a difficulty. Furthermore, the idea that there just be 3 particles is contradictory to the ideas of relativity and so on, which imply the existence of particles and antiparticles. And when there are 3, there should be possible for the forces to produce pairs of particle-antiparticle in various numbers. So there should be not just 3, but many more. So the infinity is not a paradox by itself. The 3 is more a paradox. Why is it so simple? Why can we get away and understand so much with just 3 when there should be an infinite number probably in there, both theoretically and experimentally? Another thing that's a little technical but very paradoxical is that we've had a rule back for atoms that no 2 electrons can occupy the same state. It's called the exclusion principle. And we thought we understood that that was necessary according to quantum mechanics and relativity. It has to be. And with the quarks, we find the exact opposite rule. 2 particles tend to occupy the same state. The exact opposite. It seems to be contradictory with principles. There are ways of escaping this all the time, only by complicating the picture. But the simplest picture, just 3, which explains everything, is self-contradictory. Furthermore, some people suppose that maybe these quarks could come apart. That would mean the prediction of new states, which consists of only 1 quark, say. If there were such a state, it would have to have a charge of 1/3 the normal charges of our objects, for example, or 2/3. And we don't find experimentally any such particles. Now, everybody's looking for them. But it looks as if they exist at all, they have to be extremely heavy. Then the problem is, very good, if they're extremely heavy, how, compared to a proton, say, how is it when you put 3 of them together, you get a light object that's not heavy, like the proton? There are technical ways of arranging it, but they're always complicated. The situation is, as it always is when we're near the answer. It looks much simpler than it has any right to be. And we have to understand that simplicity. And why we think it must be more complicated. Our minds are complicated somehow. Just like the orbits of the planets, which were supposed to be circles, which looked simple. Then they were experimentally, they weren't circles. So they made circles on circles on circles on circles. Got more and more complicated. Turned out it was really much simpler. It was a force inverse is the square of the distance, which made ellipses and so on. But a different way of formulating entirely, which was beautiful. So now we have our wheels within wheels. It looks simple. Nature is no doubt simpler than all our thoughts about it now. And the question is, what way do we have to think about it so that we understand its simplicity? That's where we stand now.
On holiday in the Pennines, Richard Feynman is paid a neighbourly visit by Yorkshireman Sir Fred Hoyle, the astronomer, cosmologist and science fiction writer. At first sight, there seems little in common between the study of galaxies and nebulae billions of miles in diameter and millions of light years old, and nuclear physics, where particles exist for only a millionth of a second. But the formation of stars and galaxies is determined on a massive scale by the behavior of the very nuclear particles Feynman studies. Hoyle and Feynman share an interest in the foundations of physics, and exchanging ideas in the local pub is always as profitable as it is enjoyable.
You agree that the quasars are in real trouble, that the very big redshifts...
I think so. I've had this uneasy feeling now for about 5 years. It looked crazy for a while, but it's like piling up of evidence all the time this way.
Each one makes a new problem.
Yeah,
every piece of evidence is the same problem in the same sense. If there were any cause for a redshift as big as that, other than recession, we'd be all right.
That's right.
But in the present physical laws, there doesn't seem to be any place for such a redshift.
That's good, that fits,
good,
that one failed.
And at the same time, the same kind of laws predict the kind of peculiar phenomenon of black holes, which we confusing.
Yeah.
And it could be that either the gravity is wrong or one of the physical laws are wrong, too. Some physical law that's involved.
Because I'm not arguing at the moment that the physical laws are wrong. I mean, you would agree that one has to push it through along these lines.
Yeah, the best way to progress, I always think maybe, is to try to be as conservative. That's what Wheeler always said. To try to be as conservative about the physical laws as possible in explaining the phenomenon. And if you continuously fail, then you gradually realize you got to change something. But if you start out by saying got to change something, there's so many ways of changing, and you don't know how it's most likely you don't have to change anything. Most of the time we succeed ultimately in explaining these damn things in terms of the known laws, but it's the cases that fail are the interesting ones.
Yeah. Yeah, it's like the old story, isn't it? The chap with the under the single lamp in the street.
Yes, that's right.
Where a passerby says, "What are you looking for?" He says, "I'm looking for my key," and they search for it for a few minutes. And at the end of these minutes, the passerby said, "Are you sure you lost it here?" And the man said, "Not at all, but unless I lost it here, I'll never find it."
Because the light's better. Yeah, we work where the light's better.
Yeah.
Once I was thinking by analogy that there was a time in the 1900s when the thought that the properties of substances were not physics. For example, they would be numbers. We would find a series of numbers, the index of refraction, that was physics. But the number for the index, that glass had an index of 1.543 and so on, that salt had another index, that those numbers, the properties of substances, would come from chemistry or something. But that it was that time it was considered a different branch. Then when the quantum mechanical understanding of the atoms was evolved, then we could calculate all these properties, and we realized that all these numbers were really part of physics. And so properties of substances became a branch of physics, whereas previously it was a sort of chemical branch. Then I wondered by analogy, and I always worked by analogy, what today do we not consider part of physics, which may ultimately be part of physics?
I see.
And I realized immediately something. We consider, at the present moment, most people consider that we study the laws of physics, that is how things go, given a certain condition, how the things behave after that. But how did they get into that condition is considered another problem. In other words,
boundary conditions.
Right, boundary conditions. We are given the conditions, the circumstances, and then it evolves from there according to physical laws. We're studying the laws.
Yeah.
It's as though we were doing a chess game again, and we're working on the rules, but we're not worrying about how the pieces are supposed to be set up on the board in the first place. That's not our business. That's the business of history, how the world evolved. Astronomical history of cosmology, how the universe exploded or did a steady state or whatever it was. It's not our business. It's interesting that in many other sciences there's a historical question, like in geology, the question how did the earth evolve to the present condition. In biology, how did the various species evolve to get to be the way they are? But the one field which has not admitted any evolutionary question is physics. Here are the laws, we say. Here are the laws today. How did they get that way in time? We don't even think of it that way. We think of, well, that is that way from forever. It's always been like that, the same laws, and we try to explain the universe that way. So it might turn out that they're not the same all the time, and that there is a historical, evolutionary question.
But how do you see it going? It's hard to speculate. Is it a continuous change, or is it something that